now. Good day, viewers all over the world. Welcome to Choidel online class. Today we want to discuss about the topic mapping. So we want to discuss about mapping. So what is mapping? Mapping is a rule which assigns an element from one set to another set. That is, if we have a set A, of course, from a set, we know that we are going, a set has element. If we have another set B, let's say this set B, the mapping is the rule that assign elements from one set to the other set. Let's say the rule is F. So in this case now, the first element A, that we have this element there, is called the domain of the mapping. Then once we perform an operation, let's say F on A, we are going to generate set of elements also in B. Then this set of elements in B is called codomain. Codomain. This first one is called domain. This is called the domain. Then this is the rule or correspondent the assigned element from this from here to this point. So mapping is a rule which assign elements, say maybe X, element X to a unique element, let's say unique element Y in the codomain. So where A and B must be non-empty. We can also have element maybe B to maybe D, then probably E to F. Okay. So this set A, this set that we have in A is called the domain. That's the domain. Then this other set B is called the codomain. So that's what this codomain. So in this case now we can say this mapping can be represented in three forms. We can say A to B. This is F. That is, we are saying that this F assign element from this element A to element from this set A to set B, or I would say F such that A to B still the same thing. It's still the same thing. Or if I use the first element here to the first element in B, I can say F of X is equal to Y. So where Y is a unique element that I'm going to get when I assign F, when I perform operation this F on X, I'm going to get the unique element Y. So these are the three ways that we can represent what we have on the board. Okay. Then this element Y, all these elements here, they are called the image. These are called the image of A. So all these elements that we have in B are called the image of the element in that we have in set A. So we should take note of that. And normally under mapping, it is expected that all the elements in the domain must have an image in the codomain. That's the rule. Everything here must be assigned to an element in the codomain. So most often time, the ones that are the elements are being assigned to are called the range. So as we proceed in the teaching, I'm going to give the definition of each of the concepts that is required under mapping. So all the subsets of the codomain, which is the collection of all the images of the elements of the domain, is called range. That is, let's say we have X, Y at the domain. We now have A, B, C at the codomain. So let's say F is the rule that assigns the elements. So if I have something like this, if I also have something like this, no, the domain, the set of the domain is this x comma y. Okay, the set of the codomain is what? A, B, C. But there's what we call range. Range, in this case now, range is just A and C. Is a subset of the codomain because all the elements are the domain. Another element is being assigned in the codomain. Like this B now, nothing is assigned to B. So though B is part of the codomain, but it's not a range. Range is when we assign element from domain to codomain. All the elements that have been assigned are called range. So that's what I want us to note. So let's just note that. So probably I'm going to give example to explain further on what we call domain, codomain, and range under mapping. Let's say example 1. Let's look at this example. Given that A is set A, which is equal to A, B, C, D, and set B, which is equal to P, Q, R, S, T. Okay. So the question now says, let the mapping F such that A tends to B, okay, be defined. Let the mapping be defined by the arrow diagram. Below. So this is the mapping. We have element A to and B. So here we have A, B, C, D. Then here we have P, Q, R, S, T. So this is the arrow diagram. So here we now have A to Q. Then we have C to P. Then we have B to T. Then we have D to Q. D also to Q. So this is what we have. So in this case now, A, B, C, D are the elements of the domain A. P, Q, R, S, T are the elements of the codomain. So how do we get the codomain? If we operate F on each of these elements, we are going to get the image at the codomain. So if you look at this now, from A, I want to start from A now. So F of A, if this mapping function, we operate it on A, what do we get? We are going to get Q. Okay. No, F of A, also F of D is equal to F of D. Because A and D, element A and D has the same image at the codomain. So F of B is equal to T. Then we have F of C. F of C is equal to P. That is what we have. So Q here is the image of both A and D. P is the image of C, while P is the image of B, as we can see on the board. So A, set A now, as we have set A, which is A, B, C, D. This set A is called the domain. It's called the domain in this. Then set B, which is equal to P, Q, R, S, T, is called the codomain. This is called the codomain in this mapping. Then there's another set R. We call that one range. Range will now be PQT. PQT. So this one is called the range. So you can see that the range here is a subset of the codomain, and that is what I want to establish. So though we have different type of mapping, onto mapping, subjective mapping, bijective mapping, but under onto mapping, the range is always equal to the codomain. But if you have one-on-one or constant mapping or what have you, then we realize that the range are the elements that something is being assigned to. Like in this example now, PQT are the only elements in B that we have that something is being assigned to. R and S are there. Nothing is assigned to R and X. So in this case now, what we're trying to say is that the element that we have under A is called the domain, All the elements that we have in B, they are called the codomain. But the element that this function or mapping assigned the element to, in this case PQT, it is called the range. So the range is always the subset of the codomain. So this image now, all these PQR, they are the images of elements in A. So let's note that. And there's this thing, there's this other concept that I want to talk about. It is called function. So a mapping is also a function, but we are going to see the slight difference now. So a mapping is also a function when digits is involved. So a function is a mapping whose codomain is a set of numbers. So a function is also a mapping. A function is a mapping, is also a mapping whose codomain is the set of numbers. E.g., so a mapping is also a function is also a mapping. Let's say x, then this is y. There's this function x there. Let's say you have 2, 3, 4, 6, and here I have 5, 7, 9, 13. So we realize that everything is being mapped into this. So in this case, it's a type of one-to-one mapping. So now, if all the elements that you have at the codomain, they are set of numbers, then we refer to a mapping as a function. So if a function is a mapping, a function is a mapping whose codomain is a set of numbers. Like what we have on the board now. How do we get this 5? We know that when we operate this function f on 2, f of 2, we are going to get the image. That's when we got that image 5. Then f of 3 gives 7. Then f of 4 gives what? 9. That's the image there. Then f of 6 gives what? 13. That is what happened. Then how do we generate this? Of course, f can be such that x tends to 2x plus 1. That is what defines this function. This is what defines this function, because look at when x equal to 2 here, what is y? 5 all over 2. That is, when you say 2 times 2, 4 plus 1, 5. When x equal to 3 here, element under the domain, what is y? 7. How do we get that 7? We say when x equal to 3, we have 2 times 3, 6 plus 1, 7 is 7. When x equal to 4, the image there is 9. Then we say 2 times 4, 8 plus 1, 9. And in that order. So it shows that the function is defined as what I have there. Or if you don't want to write, you can just say f of x is equal to 2x plus 1. You know, when we want to, we can write it either in this form or in this other form. So let's note that a function is also a mapping. But the only difference is that the codomain, it will be a set of numbers. That is when we are operating with digits, not letters. Then we are referring to a function, a DAR mapping as a function. Okay, so let's just take note. Let's take note of that. So, but we have to note. Let's note that. Let's note. We should note that if we have something like this now, let's say set x and y, and if this is the function, so if you have p, q, and r, and we have c, e, f, and g. So if p is being mapped into e and r to f, let's look at what we have on the board. In this case now, this relation or correspondence, this relation f, in this case, is not a mapping. It's not a mapping because this element q does not have image. So it does not make sense. Under mapping, all the elements of the domain must have image. There must be, if every element here must have a unique image and the codomain. The image might not be unique. 2 elements, or even all these 3 elements can have 1 image, is allowed. But it is not proper when we have element here that does not have image. So this type of example now, this f, this correspondent, or this f that we have here now, in this case now, the relation f is not a mapping. This relation f here, because in this case now, when we say f of p, that is, here, if we say f of p, that is, if f, this relation operates on p, the image is e, If you say f of r, if you operate on r, f of r, the image is f. But f of q, this f of q has no image, no image. This f of q now does not have any image here. So this is not a mapping. It's not a function. For us to be able to get a function or a mapping, every element that we have at x, every element here in the codomain, in the domain must have an image in the codomain. So the image might not be unique, but in this case now, because this one does not have image here, then this is not a function. It is not a function. The second one that we should take note of is when we have P. Let's say we have set P to, let's call the relation G. We can call it anything. Set P to Q. So if you have, let's say you have element U, V, W here, then we have element X, Y, Z here. Okay. So in this case now, let's say U has image W, Y. W also have this image. Okay. Then V have two images here. So what can we say about this relation G? Here, F is not a mapping. So this rule here does not hold because one of the elements of the domain does not have image at the codomain. In this case also, what can we say about G? G, which is the relation, is not a mapping. This G also is not a mapping. So the relation G is not a mapping. Why? Because one element at the domain cannot have two images at the codomain. So it does not make sense. Okay. But two elements here can have one image. Of course, we can say U. In this case now, we can say G of U can be equal to Y. Okay. We can say G of V can also can be equal to Y. But one element here cannot have two images. It does not make sense. So these are the two conditions that we have that we say the relation is not a mapping. So please let's take note. So in these two cases, let's take note that it does not make sense because here now, in this case now, we can, this is what we say f of V now will be equal to X and Z, which does not make sense. But it is possible to have two elements here that will have single image, we have one image at the codomain, but you cannot have one element here that will have multiple images. It does not make sense. So in these two cases, it's not a mapping. Why is it not a mapping? Here, element here does not have image here. Then here, one element here have two images. So let's take note that the two important conditions that must be satisfied if a relation is to be a mapping or function are, that is, if this relation, which is F here, and this relation is G here, for F and G to be a mapping or a function are, the first condition is that every element of the domain has an image in the codomain. Every element of this domain must have an image in the codomain. That's the first condition that must be satisfied. Then the second one is that the image of every element of the domain is unique. That is, the image of every element of the domain is unique. So one element cannot have two images. No, it does not make sense. But we can have two elements here that will have one image. That is fine. Even 3, even 10 can have one image under constant mapping. It's possible. But it is not possible for two here to have different images at the codomain. So these two conditions must be satisfied. So a mapping might sometimes be regarded as a set of ordered pairs. That is, we can have something like, say, X, just like in this case now, where we have P. We can have something like P. And what is P here? Is E. Can be equal to F of E. So the mapping can also be written in this form. It can be ordered pair. So let's take note. So we have seen two conditions now that will make a mapping or function not to be defined. When an element here does not have image, and when one element has multiple images at the codomain. So that nullifies the condition for a function or a mapping to be defined. So we have taken we've taken note of that. So now I'm going to talk about types of mapping. Types of mapping. So basically, we are going to talk about just 5 types of mapping. The first one is called injective. The first mapping is called injective, or you can call it one-to-one mapping. So that's the first type that we talk about. So we talk about the first type of mapping. The first type of mapping is called injective or one-to-one mapping. So in this case now, if you are given, let's say we are given, if you are given a mapping f such that x to y, of course we know the meaning of this. If you are given this, and if you are able to get that, and if f of, let's say, x1, first image, is the same thing as f of x2, which implies that x1 is equal to x2, or when x1 is not equal to x2, then this implies that f of x1 is not equal to f of x2. Okay, then the mapping f is called injective or one-to-one mapping. So that's the condition. That is the condition. So one-to-one simply means one image and one element at the domain will have a unique element at the codomain. So two elements at the domain cannot have a single image. That is what this is talking about. That is, it must be one-to-one. So I'm going to give just I'll give one example to buttress the points, so that if you don't understand all this my definition, then you understand what we're talking about. Let's say example 2. I want to give example under one-to-one mapping. Let x be a set. Let x be a set of real numbers. We have discussed about real numbers. A set of real numbers, and f is such that x equal to x. This is the relation. A mapping is a mapping defined by f of x is equal to 2x plus 3. So the question is now, is f a one-to-one mapping? So it's a question. Is f a one-to-one mapping? So we are the one that will generate that. So in this case now, let's say we have, this is x, then the codomain is y, then the relation is f, and that relation is defined as what? F of x. When f it operates on each of these, we are going to get this codomain. But let's give example -2, 1, and let's say 3. So when it is -2 here, what will be the range here? So if we decide to pick out this element now, then y, the element y here will be f of x. That is this what I'm saying. If I have this element -2, what is my f of x, which is the image here? F of x will be f of x is equal to 2x plus 3. So if my x is -2 here, so f of -2 will be the image here at the y. That will be 2 times -2 plus 3. -4 plus 3, that's -1. So I'm going to have -1 here. Then that simply means that this is to this. I'm going to have -1 here. This will be the image here, -1. When x, x belongs to this, is an image under the set. So f of 1 will be 2 times 1 plus 3, and that will be 5. So I'm going to get 5 here. Then this is the image. Then when x is 3, that's 2 times 3, 6. I'm going to have 9 here. I will have 9 there. Okay. So what would now be our conclusion? Just say, since every element in x, every element, like we have -2, 1, 3. Every element in x has a distinct. Every element has a distinct image in y. The mapping f is one-to-one or injective. That is, we are able to show that it is one-to-one. One element here has only unique element here. It's one-to-one. But at times it's supposed to have two elements here that will have one image. But in this example, it's one-to-one. So we conclude that this mapping is one-to-one because every element under x has a unique element in y, as I've shown it there. So that is the example of one-to-one mapping. One-to-one is one element to a unique image. So the second type of mapping that we are going to talk about is called the subjective. We call it subjective or onto mapping. So it is called surjective or onto mapping. So under surjective or onto mapping, so under surjective now, it is possible to have one element at the domain that will have two elements at the domain that will have just a single image at the codomain. That is under this now. What do we have? If we are given a function x to y, so if we are given that relation, so if every element of the codomain, like for example, the codomain is y, of the codomain is an image of at least one element in the domain, then that f is called onto or surjective mapping. So that's what we have. That is, the range of an onto mapping is equal to the codomain. So under an onto mapping, the range is equal to codomain. But under one-to-one mapping, it is not compulsory that the range is codomain. Once the range is equal to codomain and is onto, is one-to-one mapping, automatically that mapping will be bijective. So let's give example under this. Let's give example. Say example 3. Let the mapping G such that S tends to Y be defined by the figure below. So this is what we have here. Now we have X, this is the domain, and we have Y, this is the codomain. The relation is G here, not F. You can use any letter. So we have X, Y, Z, W. X, Y, Z, W. Then here I have E, F, G. So what do we have there? We have X to G. Okay. We have X to G. We have Y to F. We have Z to E. Then we have W to F. You realize from here now, we realize that both elements Y and W has the same image at the codomain, which is not allowed under one-to-one. One-to-one is one element to one image. That is the condition. So in this case now, we realize that f of x, that is the image of x, is what? G. The image of the f of y now, the image of y is the same thing as f of the image of y is the same thing as f of w, and it's equal to f there. No, G. The relation here is G, not F. The relation is G. Then what else? We now have Z. We have Z. So G of Z is equal to E. So look at, we're able to see two elements here that have the same image at the codomain. Not only that, all the elements in this codomain, something is being mapped into Y. So in this case now, we now conclude. We say that the range. So in this case now, the range is equal to the codomain. We say that the range of the mapping, the range of this mapping now is equal to the codomain. Is equal to the codomain, that is G of X. That is when we perform the function on the whole element here, the result that we get is Y. The result that we get is Y. So hence the mapping is onto. So in this case now, this mapping is onto. Why is it onto? All the elements here have image at the codomain, and all the elements here, something is mapped into it. So in this case now, we can define that these are relation. If we perform it on all the elements, how many elements we have here? 4. All of them have images at the codomain. Not only that, in this case now, the range, we have defined range from the onset is equal. It's a proper subset of the Y of the codomain. So if this condition is satisfied, then we say that the mapping is onto. So we move to the third one, which is called the bijective. The third type is called bijective mapping. So what is bijective mapping? Under bijective mapping is when we have F such that S tends to, that is when we have a relation F. This relation is bijective. This relation is bijective mapping. Is bijective mapping if it is both one-to-one, which is if it's both surjective and onto. Let's look at this one. Under bijective, this F, the relation must be surjective, which is one-to-one, and it must be onto. So it must be injective is one-to-one, and it must be surjective, which is onto. So if the two conditions are satisfied, then we refer to that mapping as a bijective mapping. That is for every element X, for every element Y that belongs to Y, there exists a unique X that belongs to X, such that Y is equal to F of X. So do you understand that the statement? This is what we are trying to say. That for every image, elements in the image, there exists a unique element X in the code in domain. Then our Y, this our relation, must be unique. Every Y must give us F of X. Okay, so like the example above, that is the example that I gave, example 3 that I gave under the example 3 that I gave. Bijective, it is both onto and one-to-one. So that example 3, let's check the example 3. That example 3 is both onto. No, example 2. Example 2, where I have A and B. A, then B. That I have -2, 1, where we have -2, 1, and 3, and I have -1, 5, and 9. This is the perfect example of bijective. Why is it bijective? It is onto. There exists a unique element. X, all these elements here has a unique image in this case. So that one first satisfied. That one satisfied the condition for injective one-to-one. Then the second one is that if this is F now, our F of A now here is equal to B. That is the range here, the element here is a proper subset of the codomain. So the two conditions are satisfied. For onto mapping or surjective mapping, every element here, something must be mapped into every element here. And if that condition is satisfied, it's so that the range is equal to the codomain. What is the range? Range is the element that something is being mapped into here. The codomain, we can have more than this. Either something is mapped to the element of the codomain or not, it's still a mapping, but provided the two conditions that we stated earlier has been satisfied. So this example of a bijective mapping, that's a perfect example of bijective mapping. Then another one that we are going to talk about is called the identity mapping. In case of identity mapping, that's the first one. Identity mapping. So in case of identity mapping, if you have F such that X tends to Y, okay, this an identity mapping is an identity mapping if for all X that belongs to X, F of X is equal to X, where X must be proper subset of Y. So this is what we are saying. This is what we are saying. That is, if we have X here, if you have X that takes elements to X, and this is F. Okay. So the element that we have here now, let's say the element that we have here is X, Y, Z. We also have an element here. Let's say Z, Y, X. So this is the relation X to X, y to y, and z to z. If this is what we have. So in this case now, it is both onto one to one, that is x to x, y to y, z to z. So it is both one to one and onto in the sense that all the elements here have something being mapped into them. Okay, so it has a unique property. In this case now, under identity mapping, it has a unique property that both the domain, in this case now, this is domain. This one is called domain. Okay, and the codomain, and the range, which is the subset of the codomain, everything are equal. Under identity mapping, element, the domain has x, y, z as the elements, as you can see on the board. The codomain, which is also x, has x, y, and z as the elements, and the range also have the same elements, x, y, z. So under identity mapping, all these three will be the same: the domain, the codomain, and the range. So all the three are equal, and that is the uniqueness of this identity mapping. Then I will introduce the fifth one, which is called the constant mapping. So we can have constant mapping. So under constant mapping, what is the uniqueness there? Under constant mapping, every element at the domain will be mapped into just single elements at the codomain, and that is what makes it constant mapping. Every element at the domain. So under constant mapping, we can have, let's say, f of c constant, x tends to y, which assigns every element x in x the same image. They are going to have the same image. The same image k is called a constant mapping. That is, for all s that belongs to s, we have f of x to be equal to k. This is what we are saying. This is the element of the domain. We have x, y, z, and the codomain, let's say y, we have k, a, b. This is the relation f. In this case now, s is being mapped into k, y the same thing, then z, everything into one image. So that's why we said f of x is equal to k. F of x is equal to k is that every element that we have here, f of x, f of y also is equal to k, f of z is equal to k. Everything have the same image. Then if that happens, then it is referred. In this case now, the range consists of only one element. So here now, the domain is equal to what? X, y, z. That's the first element. The codomain y is equal to k, a, b. But here the range will have only one element, k, because range under codomain is the image that is something, is the element that something is being mapped into. So here now, the range is not like the other one that we did discuss, the identity mapping, that everything is equal. Here, the domain is different from the codomain, and the codomain, the range here is just a subset of the codomain, just one element out of the three elements of the codomain. And that's what we are going to have here. So I've been able to introduce mapping and the three and the 5 types of mapping. So let me take one or two examples, then we close the class for today. So we continue from there. We'll continue the concept mapping from there in our next class. Let's say example 4. So in this case now, the question says, let x equal to a, b, c, d, and y is equal to p, q, r, s, and relation f to y. A mapping defined by the diagram. This is x and this is y. So this relation is f. We have A, B, C, D. Then we have P, Q, R, X. So we have A and D to X, A and D to X, okay? Then B and C to Q, B and C to Q. Okay, the question now says, find the range of the relation F. Of course, it is very simple. The first question is that, is this diagram a mapping or a function? Yes. Why is it a mapping? Every element at the domain here has either unique or, but at least it has something that is being mapped to at the codomain. That's the first condition. And the second condition is that every element here has just, it is one element. You can have multiple elements. No, two elements does not have, one element does not have two images here. So the two conditions that is has to be satisfied. So here, this is the domain, this is the domain, this is the codomain. From what we are given, we are asked to find the range. The range here now will be what? Q, comma X. That will be the range, because the range is just is something that is what is the element that something is being mapped into. So in this case now, P and Q they are just there. They don't have any problem. So here now, this is what we are going to get. The range will only be Q and X. P and Q are free. No, nothing is being mapped into them. Okay. Then I will take the last question. So we are going to continue from here. So this is what we are going to have. Well, let me just now. So if you have further questions on mapping, just type at the comment section. I promise to attend to it. But today we are define what a mapping. What is a mapping? That is, we define mapping. We have been able to define mapping. In today's class, we have been able to define mapping as a rule which assign an element from the domain to the codomain. Then this relation is what we assign this element from the domain to the codomain. Then all the elements all the elements at the codomain that something is being assigned to are called the images. Okay, and we know that, and those elements are also called the range. So we have also been able to establish that there are 5 types of mapping. So we have gone through the 5 types. The first one, we have talked about the first mapping, which is called the injective or one-to-one. That is relation one-to-one, one element to one image. Then we've talked about the subjective mapping, which is called onto. In that case now, we realize that the range is equal to the codomain. Then the third one is when we have bijective, that is when the mapping is both onto and injective and one-to-one, both subjective and injective. Then we also talked about identity mapping. That is when the element that we have in the image, the element that we have in the domain will replicate itself at the codomain. That's identity mapping. Then we talk about the last one, which is called the constant mapping. Under constant mapping, all the elements that we have in the domain, we have a single identity element. We have the single image at the codomain. So I'd love to stop the class now because of our time. By the grace of God, we are going to continue from there in our next class. Thank you.